Okay, in this example, we're told we have a hypodermic needle, and it has an inside diameter of 0.1 millimeters and a length of 25 millimeters, and it's used to inject saline solution with a dynamic viscosity 5 times that of water. The plunger diameter is 10 millimeters, and the maximum force that can be exerted by thumb on the plunger is 45 newtons. We're asked to estimate the volume flow rate of saline that can be produced. So this is going to be a pipe flow style problem. Let me draw a sketch of it. So we have our needle. That's this kind of long section here. Let me just call that length L. It has a certain diameter, little d. That diameter, little d, is the 0.1 millimeters, and the length L is 25 millimeters. And this section over here is the plunger. And we can apply a force F of 45 newtons, and that diameter, we call it capital D, is 10 millimeters. And we know the dynamic viscosity of the saline is 5 times that of the dynamic viscosity of water. So the dynamic viscosity of saline. Okay, so this, like I said, this is a pipe flow problem. We're really trying to get relate the flow rate through this pipe as a function of the pressure gradient that's applied. So physically what's going on here is we apply a force on this plunger. That's translated into a pressure because we have a force divided by the area. So we have some pressure here. The pressure right at the outlet here is going to be atmospheric pressure, right? So we're going to do things in terms of gauge pressure. So it's 0 gauge pressure over here, and it'll be 0 gauge pressure at the outlet. So we're going to have the pressure right on the piston face will be the force divided by the area of the piston face, right? So that's the pressure being applied right at this point right there. Let me erase the other. Oops, went too far. Okay. So that's the pressure just right at the upstream side, or right on the right-hand side of the plunger. And then we're going to assume that this plunger section is very small. It's negligible. We don't really know any information about it anyway. What we're going to do is just focus on the flow inside this narrow section. Okay, so in order to find the flow rate through this small needle, the first thing I'm going to do is I'm going to assume that the flow in there is laminar. And the reason I'm doing that is because I expect the Reynolds number in here to be very small. Recall that the Reynolds number for a pipe flow is the average velocity times the diameter of the pipe divided by the kinematic viscosity, or we could write it in terms of density and dynamic viscosity if you prefer. And if you look at the conditions for this case, the diameter is quite small, right? So we're talking about 0.1 millimeter. So that's going to make this Reynolds number pretty small. The velocity through this pipe we also expect to be relatively small. We can calculate what that is in just a little bit, but I don't anticipate that to be a huge number. And then the density, it's about the same density as salt water, and the dynamic viscosity is pretty large. It's 5 times greater than that of regular water. So I just anticipate this Reynolds number to be less than 2300, which is the critical Reynolds number dividing laminar and turbulent pipe flow. So I'm assuming that that's the case. I don't know for sure yet because I don't know what this average velocity is, but I'm gonna guess that that's the case because it's such a small diameter needle. Okay. So with that in mind, we can relate the average velocity and the pressure gradient. If you go back through the notes and you look at the derivation for Poiseuille flow, so Poiseuille flow, let me write it out here. So Poiseuille flow is laminar flow through a circular pipe. You can derive that from the Navier-Stokes equations, but if you go through the notes on that topic, you'll see that the average velocity in the pipe, let me put it as V bar, average velocity in the pipe is the pipe diameter squared divided by 32 times the dynamic viscosity times minus Dpdz. This is the pressure gradient, where Z is this distance heading downstream in the pipe. And the minus is there because the pressure is highest here and lowest here. So the pressure is decreasing here, so the pressure gradient would be negative. So a negative times another negative makes it a positive. And if we want the volumetric flow rate, because we're asked here to find the volume flow rate, not the average velocity. But if you wanted the volume flow rate, that's just going to be the average velocity times the cross-sectional area of the pipe, right? So we could do that. And if I just substitute in right there, this will come out to be pi times d to the fourth all over 128 times the dynamic viscosity times minus Dpdz. So that's how I'm going to find the volumetric flow rate. So let's first of all calculate this pressure gradient, Dpdz. So Dpdz, we're going to say, is equal to the change in pressure all over the change in length, L. Change in pressure is just going to be that force that we apply. Actually, let me take that back. That's going to be, the change in pressure will be the pressure at the outlet minus the pressure at the inlet divided by the length, right? And the pressure at the outlet is 0 because it's atmospheric pressure right here, right? It's a free jet coming out of the pipe, so it's 0 gauge pressure. And at the inlet, the pressure is going to be this force divided by the area. So force divided by the pi capital D squared over 4. And then the length, it's just, you know, the location here is L, the location here is 0, so that's why we end up with an L there. So that's how we find this pressure gradient. Mu, we know, is about 5 times the density of just regular water. So this comes out to be about 5 times 10 to the minus 3 Pascal seconds. The other dimensions, you know, we have here. So we can plug all of these things in to this expression here using this for our pressure gradient. If we do that, we'll get the following numbers. So Dpdz comes out to be minus 2.29 times 10 to the 7th Pascal per meter. We'll get the average velocity. So if we then use that in this expression, we can get the average velocity comes out to be 1.43 meters per second. So it's not a super small value, but it's also not super large. And then the volumetric flow rate comes out to be about 11.3 cubic millimeters per second. So that's what we're trying to find. Now, I had assumed along the way that the Reynolds number was small. So, you know, this expression that I wrote here is really for a laminar flow in a circular pipe. So if the flow was turbulent, I should not use this expression. This is only valid for a laminar flow. And so I assumed it was laminar, right? So I need to verify that it is indeed laminar. So now that I have a velocity, I can take that velocity, plug it in up here. I know my little d, that's given right up here. I know the dynamic viscosity, that's given right here. The density, I'm just going to assume that the density of saline, it's pretty close to the density of water. It'll be a little bit higher, but it's pretty close. But let me go ahead and use these values to calculate the Reynolds number, just to verify that we do indeed have laminar flow. When I do that, it comes out to be about 28.8. So you can see that I'm well within the laminar flow assumption here. So this 28.8 is much smaller than the 2300. And again, the reason this is so small is because that diameter is small. We're dealing with a very narrow diameter, so we'd anticipate the flow being laminar. Since my assumption of laminar flow is consistent with my solution, everything's fine, and so I made the right guess. If it had turned out that this Reynolds number was over 2300 and that we would have turbulent flow, then I'd have to go back and modify my solution. And I won't go through that because this is a flow through hypodermic needle. It's not going to be turbulent. Okay, so I think that covers everything here. The key thing in this problem is just to recognize that we're dealing with a laminar flow, and so we can use the expressions for a velocity in a laminar circular pipe flow. So that's how I went through this. Okay, we'll end it there.